Hey, it's Papa, reflected in the sliding glass door. This is a follow-up video to the GH3 video about the rift to drift sequence after Rodinia rifted. I want to correct some errors that I made and also add some stuff to that that'll help make things more understandable, I hope. So here we go. You remember this picture? And I showed you this big piece of land crust that broke loose and drifted out into the Proto-Atlantic Ocean that was forming after the rift. Well, I didn't tell you what these mean. IP means Interpediment, and that will be recognizable to you as one of our geologic provinces of Georgia. And you can go back and look at that in the last video and see just where the Interpediment is. This EBP is mislabeled. It should be EBR. So I'm going to do the R part. EBR stands for Eastern Blue Ridge. And that is also one of our geologic provinces of Georgia, and you can go back and look at that. You're going to notice that the Interpediment is up here and the Eastern Blue Ridge is down here. Coming up in the next video, we'll find out how they all got mashed together. So that's mainly what I wanted to tell you about that. Also, I mentioned that Chilhowie Mountain is an example of that, the ancient beaches that were distributed across the whole United States as the ocean rose after rifting. Well, okay, if so, why is it a mountain now? Why does it not look like a layer of sandstone? That is a good question, Papa. I'm glad you asked it. The reason is that since that great sand beach layer was laid down in early Cambrian times as the ocean rose, there have been tremendous amounts of mountain building and crashing where huge island arcs and microcontinents and entire continents crashed into the eastern United States, and it piled the Chilhowie sands up into the mountain that we see now. Let's see, what else? I talked about the fact that as the sea rose, these beaches covered the whole United States, and then the layer of mud that came after covered the whole United States, and the layer of limestone that came after covered the whole United States. That is true. And as an example, I cited the Bighorn Mountains. But I cited the layers. I named the layers wrong. The sand layer, the ancient beach layer, is in fact the Flathead sandstone. But the mud layer that came next and turned into shale is the Wolsey shale. The limestone layer that came after that is in fact the Gallatin limestone. Another example, if you go to the Grand Canyon, you can go down way toward the bottom of the Grand Canyon, you will see a layer of sandstone called the Tapeats sandstone. That's the same beach, a layer of beach sand that was laid down. And you see, as the ocean rose, the sand beach kept migrating uphill, and so it migrated across the land, and the shale migrated across the land, and these three layers cover the whole United States. Grand Canyon, start off with the Tapeats sandstone, which is the ancient beaches, and then comes the Bright Angel shale that came on top of that. And then on top of that came the Mauve limestone, same layers. Also, I showed you examples of rocks, but I forgot to show you an example of marble. So here is an example of marble. I don't know if you can see how it kind of, how it kind of sparkles in there. That's the calcite crystals. Calcite is the mineral that is made of calcium carbonate. This is marble from Murphy Marble Formation. And if you may have heard, if you go to Tate, Georgia, which is in the middle of the Murphy Marble Belt, you will see what is called the Pink Palace there, which is a huge mansion built by the fellow that first began to quarry the Murphy marble and turn it into mostly into floor tiles and wall tiles. And that whole giant mansion is made of pinkish Murphy marble. It's gorgeous. And you can actually go to the office. The quarry office is still there, right behind the mansion, or maybe a little bit to the left of it. You can go there. They will let you go into the marble stockpiles, and purchase squares of this Murphy marble. And it comes in a pinkish variety, which is beautiful, and a really white, marbly, quote unquote classic marble shape color. And it also has a white marble with black streaks in it. It's really gorgeous. And you can buy those. I think they're like $1 a square, and the squares are 1 foot squares, so you can get a really good collection. I got a nice collection of them several years ago, but they've been sitting out in my yard and they got really dingy, so they're not worth just showing you. But let me see if I can. Well, we'll let this be the example, and you can scratch this with a knife. It looks like quartz, but it's not, because you cannot scratch quartz with a knife. Also, if you scratch off a powder, even if on the marble, and put it in, vinegar, it will fizz. And that's how you can tell marble from quartz. Isn't it beautiful that this old gray limestone, under metamorphic pushing and shoving pressure, turns into this gorgeous marble? It's a beautiful quarry stone. Okay, what else did I want to tell you? Oh, I wanted to tell you, after rifting and the rift-to-drift sequence occurs, you get what is called a passive margin, and that's what we have today off the coast of the eastern U.S. It's a passive margin. That means everything's quiet, no rifting's going on, and no mountain building crashing and smashing is going on. It's just quiet out there, but that's not going to last long, of course, tectonically speaking. This is what the passive margin looks like. I hope this is clear. This is land crust. Mostly it's made out of granite. It is sitting right next to a layer of ocean crust. Ocean crust is made mostly out of basalt lava. The two kinds of crust, land crust and ocean crust. Those are the only kind of crust that exist on our planet. Well, when you have a passive margin, what develops is, and this will sound familiar, you have a shallow continental shelf that might go out 300 miles out into the ocean. And, it gets deeper as you go. It might be, I don't know, limestone probably has to have about 400 feet or less to grow. And really and truly, the shelf probably goes out further than the limestone does. But for this drawing, we're going to do it this way. You've got the sand, the coastal plain sands and the sand beaches. And that sand layer goes below that because the ocean rose to create this passive margin. In between that, you've got a layer of shale, which starts off as black mud. The mud is finer particles than the sand, so when the river dumps all this stuff out, the sand falls down first and creates these beaches and the barrier islands. And then the small shale, the small particles that make up mud can float out deeper, and so they settle down out deeper and settle on top of the sand. And then when you get out even deeper past where the mud is deposited, the water is clear, and if it's warm and fairly shallow, you get a layer of lime-rich mud. And then over time, and with pressure, as the layers build up, they push down on the layers below, and you create rock. And in this case, the limey mud becomes limestone. The black dark mud becomes shale, and then the sand becomes sandstone. Then you have the continental slope. That's where the edge of the continent crust drops off right down to the deep ocean, which is here. And this is where the turbidites form. This is where stuff from up here goes tumbling down and gets all mixed up size-wise. And we've seen turbidites. Great Smoky Mountains is one huge turbidite reserve. Turbidite sandstone and greywacke is a kind of turbidite that has smaller particles. As you remember, turbidite sandstone and these turbidites are, you have a matrix of sand and mud, and within that matrix, like raisins in a muffin, you have larger hunks of quartz and feldspar, and even some small granite particles, all mixed up size-wise, and that's what turbidites are. So when you see turbidites, and that's these turbidites is where our Cholula Gorge rocks came from. So the rocks of Cholula Gorge at one time were on this continental slope that formed after the rifting of rhodinium. Out here in the deep ocean, it's way too deep and way too cold for limestone to form. But the finest particles of silicon can get washed way, way out here, and they form chert, which is flint is the same thing. You all know what flint is, what they make the arrowheads out of. What flint is just a dark color of chert. And this chert forms. The particles are so small, the crystals that form are microscopic, and they call it cryptocrystalline. And it forms these layers. You get a layer of chert and a layer of very fine, maybe dark mud, layer upon layer. And when you look at it, when it gets pushed up on land, which it will get pushed up on land with mountain building, mashing and crashing, it's called ribbon chert. And if you go out to California in the Coast Range, as you travel through there, you will see a bunch of ribbon chert piled up in piles because of the mountain building that's been going on out there. If you go to the Sequoia National Park, Kings Canyon actually, and you go way back into Kings Canyon, you'll see some of this ribbon chert folded in the walls of the canyon. And then underneath the ribbon chert, you have basalt lava, which basalt lava is ocean crust. Basalt lava, below that is gabbro magma, and below that is serpentinite, actually kind of mixed in. And below that, which I haven't shown here, but it's below all of this, is the molten magma of the mantle. And that molten magma of the mantle is made mostly of peridotite and dunite, which are there's more of that on the earth than any other rocks. Okay, I think that's all I wanted to say. Oh yeah, also I talked about the Kanasaga shell, also its Rome shell, that red colored shell, but I didn't tell you why it turns red. If it's full of iron and it spends a lot of time in dry riverbeds on its way to the sea, then air oxidizes the iron and turns it red. It doesn't have organic matter in it because there weren't any trees or bushes, or was no vegetation on the land, and organic matter turns the shell dark colored. And so that's that part. Okay, I hope that makes sense. I'm going to have some lunch now. Papa out.